Greetings. Today we're going to talk about the instantaneous rate of change of a function. So let me just write that down up here. So we're talking about the instantaneous rate of change. So previously we saw the average rate of change. So the average rate of change we said was equal to f of b minus f of a divided by b minus a. The average rate of change is defined over a specific interval. In this case, it's the interval from a to b. So over a specific region or interval in the independent variable, you would say what is the average rate of change over that interval. Now the instantaneous rate of change is a little bit different. It's at a single point. So it will be the instantaneous rate of change of a function f, so let's say of f of x, at one particular point, so at x is equal to a. So the analogy would be as follows: average rate of change. So here let's think about x of t being just your position or your distance that you traveled at time t. Right, so the average rate of change, as we saw in a previous video, is just simply the average speed. So for example, 76 miles per hour was an average speed, was the average speed between 3:30 p.m. and 5:45 p.m. Right? So the instantaneous rate of change is an instantaneous speed. It's the speed at one moment in time. So you look at your speedometer at 3:45 and 12 seconds and it says 80 miles per hour. Your instantaneous rate of change at that point in time is 80 miles per hour. So it would be your speed at one instant in time. And of course, the independent variable does not have to be time. We saw examples with the average rate of change where the function was density of seawater as a function of the depth. So in this case, it would be at one particular depth, what is the instantaneous rate of change? So how much does the density of seawater change going from a certain depth to an infinitesimally small amount deeper in the ocean? So how do we understand what the instantaneous rate of change is? How do we define this mathematically? And to do this, we'll use the average rate of change. So the whole idea of the instantaneous rate of change, it's basically defined or computed by taking or computing the average rate of change over a sequence of smaller and smaller intervals. So a sequence of smaller and smaller intervals, each containing the point x equals a. So how we understand the instantaneous rate of change is by taking the average rate of change over this smaller and smaller sequence of intervals. And eventually the rate of change will level out to the instantaneous rate of change if the instantaneous rate of change is actually well defined and exists at that point. So let's see an example of this. So let's suppose that, let's stick with the position and velocity example. So let's say x of t is your position as a function of time. And let's add a little story to it. So let's say that we have the Empire State Building. So I'll just draw it. It's not so it's just a tall building. And you're standing at the observation deck. And don't do this because you can kill somebody, but suppose you drop a penny off of the Empire State Building, and we're going to neglect air resistance. Well, the height, so in this case position will be the height, x of t, in meters, t seconds after you drop, let's say, a small pebble or something, or a penny, drop a particle, is given by the following formula. So x of t is going to be 380 minus 4.9 t squared. And this is in meters. And this is t seconds after the drop. Now, to find out how long it takes for the object to fall and reach the ground, you can just set x of t equal to 0. Few things to note of this. X of 0 is equal to 380 meters. So this would be the height at which the object is dropped. It's the initial height at time 0. To solve for the point in which the penny or the pebble reaches the ground, we can set, well, x of capital T is equal to 0. So here, capital T is the total time of the fall. So x of capital T is equal to 0. So we have 380 minus 4.9 capital T squared is equal to 0. You can solve this, and you see that capital T is approximately 8.8 seconds. So let's choose a point in time before the particle reaches the ground, maybe after 5 seconds. So what is the particle's instantaneous speed after 5 seconds? It's supposed to be a 5, like that. Okay. So the formula again was just 380 minus 4.9 t squared. And so we want to estimate the instantaneous rate of change at t is equal to 5 seconds. So what we'll do is we'll compute the average rate of change over some smaller and smaller intervals. So we can make a table. So here's t, and here's x of t, and we can compute, 5, 5.001, 5.01, 5.1, and 6. So at different moments in time, we can compute, so this is time in seconds, this is x of t in meters, we can compute the height of the pedal. So at 5 seconds, we would be at a height of 257.5. So I just plugged in 5 seconds for the formula. At 6 seconds, I'm going to skip ahead to 6. At 6 seconds, we are at a height of 203.6 meters. So as I do this, let me make a second table, and this table will be an interval and then the average rate of change. So the first interval I want to include is the interval from 5 to 6. So here the average rate of change over the interval from 5 to 6 will be the difference in the outputs divided by the difference in the inputs. So just to do one explicitly, the average rate of change over the interval from 5 to 6 is going to equal x of 6 minus x of 5 divided by 6 minus 5. So that's going to equal 203.6 minus 257.5, which gives me negative 53.9, divided by the change in time, which is 6 minus 5. So the average rate of change over this interval is minus 53.9 and it's in meters per second. Now let's look at the interval from 5 to 5.1. So first of all, the average rate of change between time 5 seconds and 6 seconds after the drop is, an estimation for how fast the pebble was going after 5 seconds. But we can do better. Let's look at 5 seconds, 5.1 seconds. That's going to be a much better approximation for how fast it was going at that one instant in time. So at 5.1, what is the height of the pebble? So we'll do 5.1 squared times 4.9 and subtract that from 380. And we see that at time 5.1, 252.551. Now the average rate of change over the interval from 5 to 5.1 is again going to be x of 5.1 minus x of 5, and then divided by 5.1 minus 5.0. So 5.1 minus 5 is 252.551 minus 257.5. That gives me negative 4.949. And then divided by 5.1 minus 5.0 is 0.1. So the average rate of change is minus 49.49 meters per second. So we see it's a little bit, it's not dramatically different than the average rate of change between 5 seconds and 6 seconds, but it is different. It's going to be a better approximation for how fast the pebble was going at 5 seconds. But we could do better again. Computing the position or the height of the pebble at 5.01 seconds, 5.01 squared times 4.9, and then subtract that from 380, we get a long 257.00951. And if we find the average rate of change using a similar methodology between 5 seconds and 5.01 seconds, we get an average rate of change of minus 49.049 meters per second. Very interesting. Let's do it once again. 5.001 squared times 4.9, subtract that from 380, and we have 257.4509951. Subtract off 257.5, divide that by 0.001, and this time we get, for our average rate of change between 5 and 5.001, very interesting pattern is emerging, 49.0049 meters per second. Now I would bet if we continued this that the average rate of change between 5 seconds and 5.0001 seconds would be minus 49.00049 meters per second. So this is a guess. So I'll write a little red G here. So you can verify and see if my guess was right on your own. But that's my prediction for what's happening. But either way, something very intriguing is happening. As we narrow down our interval to be smaller and smaller and smaller, the average rate of change isn't varying dramatically. It's leveling off at one definitive value, which is negative 49. So we can say that by just looking at the pattern, we can say that the instantaneous rate of change of the height, so this would be the instantaneous speed at that moment in time, is approximately, I believe this is actually exact, but since we only have a series of approximations, we have to say it's approximately 49 meters per second, with a negative sign indicating that the height is decreasing. In fact, this is at 5 seconds. Yeah, it's going to be exactly. And if we looked at the time in which just out of curiosity, the time in which the object lands, which I said was approximately 8.8 seconds, the speed will be about 86 meters per second at the time that it hits the ground. Now 86 meters per second, you can convert that to miles per hours. Don't have a conversion table handy, but it's probably pretty fast. Let's just go to Safari. Meters per second to miles per hour. So let's see, 86.3, about 200 miles per hour. So you don't want to throw a penny off of the Empire State Building. Neglecting air resistance, it's going to hit the ground going almost 200 miles per hour. If it lands on somebody, it will probably kill them. So make sure not to throw pennies off of the tall buildings. So that is our first example of computing the instantaneous rate of change of a function.